Hello, I'm Mitchell from the Ohio State Underwater Robotics team. Today I'm going to be taking you through our team's software setup for our control system. It's built to be a cascaded P controller, and I'm going to be showing you guys this diagram that'll give you a better understanding of what's happening behind the scenes. So to build the trajectories our robot's going to follow under the water, we're using ROS Move It. Move It creates a trajectory where each point inside of it has an X, Y, and Z value associated with it. So basically our robot would follow along and reach each point in that trajectory to reach the end goal, which is the final point in the trajectory. So basically how that works is, so Move It would be up here in the diagram outside of the view. From there, it's going to feed it, the Move It positional data is going to feed into a node we've written that'll derive velocity and acceleration, linear and angular velocity and acceleration from that positional data in the trajectory, and then from that read-in value, those read-in values is going to feed into our controller setup. Inside the controller node, we have to do math to account for linear and angular data. So in regards to the linear, we basically just compute desired output force. To do the math, we take into account desired position, velocity, and acceleration at that point. Do some math that combines the values with different weights for a final output force, and then for the entire robot body. And it's basically the same idea for angular. It's gonna take the position velocity acceleration and break that down, do some math on it to get the desired torque, and then from there we have a final node that will solve based on the body the body desired outcome. So, and then it breaks it down so what each thruster on our robot needs to output to get the desired state of the robot at that point. So yeah, that's basically the overall structure of it. Let me take you guys into RViz. So RViz is basically just going to demonstrate what Move It's doing behind the scenes to build the trajectory. So it sees that the robot is pointing up in this state right now, sticking out of the water slightly with its front facing up, and it wants to put the robot in this, where it's darker here, it wants to put the robot in this state, so where it'll be like facing up underwater. And you can see this is true. The whiter robot is the current position. You can see that's true. If we go to our topic monitor, this is the sky here, and this is the water, and the robot's sticking out of the water, pointing up slightly. So what I'm going to do is go back into RViz. Let's go ahead and plan this. So it's going to take this robot where it currently is and try to get down to here. Oh, so actually it'll be facing downward then. So it'll be looking straight at the ground. And we can see how it'll try to do this. So we have it planned out. So basically just built a trajectory that's going to start feeding into our translator to get the velocity acceleration that feeds into our controller, and then it feeds into our thrust solver so that each of the 8 thrusters on the robot reaches its desired position. Okay, so let's go ahead and execute this. We'll see it start moving then, very slowly. And then let's go into topic monitor so then we can see it moving in real time in the simulation. So there we go. It's starting to point downward. Should just keep going. So then we can see it again in RViz. It's going to start to slow down now as it's almost in its desired position. Switch back to the topic monitor. And it's kind of dark, but you can see it's just pointing straight at the ground now, which is what we desired it to do. So let me go ahead and take you through the diagram one more time now that you've seen all those features working together. So this is a cascaded P controller, meaning it's basically leveled on top of each other, where it does the similar operation for position and then velocity and then acceleration to get a very precise value of where we want the robot to be at that point in time. So once again, RViz was demonstrating what Move It is doing behind the scenes to build the trajectory where each point, we want the robot to reach each point at each point in time. So from those x, y, and z values, and then the x, y, z value, and then the quaternion angular position, we're going to derive velocity acceleration. We need all three of those for the linear and all three of those for the angular controller. And then does a computation and takes all those values into account for the desired output force and torque on the robot body. From there, we need to do some more computation to get the desired output for each thruster on our robot, in a manner that's going to be efficient, so that each thruster is doing a similar amount of work, and it's in a way that it's actually possible for the robot to achieve that state, the final state we want it to be in. So yeah, that's pretty much all there is to our control system.